So we'll get back to this in just a minute there. And to give a little time for those things to possibly come in, we can see if there's any homework questions. Do you guys have any questions on the homework let's do this Sunday? This point?
Yeah, I don't think so.
We're not quite through all the content here, but we're close. We're through most of it.
Number 6, whenever I ask you to find, determine if the lines are parallel or identical, how do you go about that?
So parallel lines, when we're talking about equations like this, when we have a parametric equations for a line, the direction vector we're given goes in the direction of the line, so it's parallel to the line there. So like for example, for L1 that's listed here, what is the direction vector for that first line?
-436.
Here numbers, -4, 3, 6. So really we're saying, okay, well, if I do that for all of these, go through and find that direction vector, -4, 3, 6. For L2, it'll be 8, -6, -12. We're going to use those to answer the question there. Parallel vectors have what in common? How do we know vectors are parallel? Scalar multiple. So once I've got all those direction vectors, we're going to look to see if they're scalar multiple to each other. Any of those vectors that are scalar multiples of each other would then be parallel. And then identical will just mean like they're going through the same point, the same line there. But if you find they're parallel, then that works for this too. Okay, parallel, identical. If they're identical, it'll also be parallel. So that will cover that there.
So would it just be the coefficients, or are we also include?
Yep, just really the coefficients there.
Okay, so we just get rid of the constants.
Well,
Constants have no
no,
impact,
the
so-
constants do have an impact here too. So parallel will be just paying attention to the direction vector, and that's good enough for parallel. What the constants do is that's how we can tell if it's identical. And it's the same thing in a two-dimensional system too. If you're talking about just lines with slope and a y-intercept, if they have the same slope, the lines are parallel, right? If they have the same y-intercept and the same slope, and they're identical. They're not going to look the same here as they might in that two-dimensional system just because we've got a whole bunch of points there. But ways you can check and see if they're identical is plug in values. If you let t equal 0 in the first one, you're going to get some points out of it. If you can go through that same point on a vector that's parallel, you know they're going to be identical as well. But since this isn't asking me to tell if they're identical or they're parallel, just kind of group them all together. Finding if they're parallel will be sufficient here. What that point does, it tells if they're identical. Right? Does that make sense? So yeah, I'd say start with the vectors, Edwin, and then look to see if they're scalar multiples of each other. Okay. All right, other questions?
Number 12.
An equation of the plane that contains the 3 points. That contains all the points are equidistant from the given points. Okay, so how can we do this one? I'll just ask you guys instead of me explain it. What would we do on this one, number 12? An equation of the plane that contains all the points that are equidistant from the given points. What does this look like right now? We just have 2 dots in space, right? Try to visualize what this plane would look like. If you've got 2 points in space and you want to find all the points that are the same distance from both these points, how are you going to do that? Like, what are they going to look like there?
Come again?
It's not going to be a square. So we've got these 2 points. Let's just graph them. -7, 4, 1. This is a good question. I like this one. It's probably why I signed. Actually, let's just open a new one of these because I want that for later. All right, so let's graph these points. And again, yours may be a little different on your homework since some of those are written in red there, but we can still get the idea.
Right in the middle of those 2 points.
Yeah, that's what I'm getting. Yep, we're going to be right in the middle of those 2 points, and then we're going to have to move a little bit to count for all the possible points. 6, -2, 4. All right, and even if I graph those wrong, just look at the idea from looking at this here. I'm going to remove that plane. Okay, so here is our kind of standard orientation there, and just remove this and consider points. So we've got 2 points, A and B, and we want to find all the points that are the same distance between them. Okay, so like what Russell said, if we just imagine connecting these 2 points to a line, halfway between those on that line is going to be equal distance from both points here. Is that the only point in space that's the same distance from both of these? No, I mean, we can go, you know, off that line a little bit, and we're still going to be able to find a point that's the same distance from both of these. So kind of what we're doing here is we're saying, okay, if I imagine connecting these 2 points here, the midpoint is going to be the same distance from both of them. But I can kind of imagine if I were to move up around here, I can find a point right here that's the same distance from A and B, right?
But it's still a plane, so it doesn't matter.
Right, and that's what we're trying to find is that plane. We're saying, okay, for this plane, how am I going to go through and find the equation for that plane there? Okay, so how can we do this?
Do we Google it?
So the one.
Do we solve for,
I could hear you guys talking, but I couldn't say what you said. Did you have an idea of how to solve it?
I thought like you solve for each of something and then you subtract something.
There's a lot of somethings there. Let's fill them in so that we know what those somethings should be. Okay. Let me add a page. Oh, I think we may have all the quizzes now too. What you said for this, the Russell, is what we want to do. All right, so we've got these 2 points. What do we need to write the equation of a plane? We need two things. We need a normal vector, we need a point. Okay, we are not given either of those yet. Okay, these points are not on the plane, so we need to find both that point and a plane still, or that point and a vector. Okay, and Russell, say what you said again. You said something before.
Point AB and then normal to.
Rightio. If we make that vector AB connecting our 2 points, that's going to be our normal vector there. It doesn't matter if you go AB or BA, it really doesn't make a difference, but the vector that connects these 2 points is our normal vector. So let's say -7 minus 6, 4 minus -2 is +6, and 1 minus 4 is -3. Okay, so we could use that as a normal vector. And again, if we go the other way, that's fine too. Okay, it's only a point though. What's our point on this plane going to be?
7.1.
No, that's not on our plane. That's not on our plane.
Between the two.
The point between the two of them, the midpoint. So we've got to go back and find the midpoint between these two things here. And we talked about how to find midpoint. It's basically just the average. So if we do -7 plus 6 is -1, -1/2. 4 plus -2 is 2 divided by 2 is 1, and 1 plus 4 is 5, so 5/2. Okay, so we're finding the midpoint of those 2 points for this guy right here. Okay. But then once we have that, now it's just a matter of plugging into the equation for a plane. Okay. I won't go through and do all that, but recall the equation for a plane is this.
I think I should.
So if we go back and plug in -1/2, 1, and 5/2 for our x1, y1, z1, our normal vector we have there. And if you did it the other way, if you found your normal vector the other way, that's going to be fine. Everything's going to still equal out to the same thing here when you simplify this down there. Okay. So there we go. Those are kind of the starting points of what you need. Plug everything in. The rest is going to be algebra there. But there's kind of the think about it.
So you find normal vector, then okay, this is pretty much what we're doing on the quiz. What do you do with that normal vector?
So your normal vector is your A, B, and C.
Right.
So -13 is going to replace A.
That's
6.
it.
That's it. And then you just reduce it.
I did cross product.
On the second one for the quiz, you have to do cross product. So if you did cross product, you might not be wrong. Okay. Let me see if I've got all the quizzes. I think I may have them. Or close. 1, 2, 3, 4, 5. Yep. I think I got it right. So after I finish with more questions, we'll go over that. Okay, so that's not the answer to this question, but that can see pretty far, hopefully, on question 12. Other homework questions?
Got it. I had the right normal vector. Yes.
All right, let's take a look at the quiz real quick here, since I think I've got all of them. And this should be pretty similar to what we just talked about, equations for a plane here. So in number 1, we're trying to write the equation for a plane. Do we have to do anything before we can start writing the equation? No, we're given everything we need there. We're given the point, we're given the vector. It's just a matter of plugging everything in and going through and simplifying it. So I'm not going to have you watch me go through and do that. As long as I didn't make a mistake when I made the key, we should get this. 2x plus 3y minus z equals 10. Does that look familiar? Okay. Now for number 2, we have to do a little bit of preparation for this. We're just given a bunch of points there. What do we have to do in number 2 before we can have the situation we have in number 1?
Find 2 vectors and then find your cross product.
We have to find 2 vectors and then find their cross product. Okay. It does not matter what 2 vectors you find. You take any pair of points and subtract them in whatever order. Another pair of points, subtract them in whatever order you want. As long as you didn't pick the same 2 points, you'll get 2 vectors there. But then find their cross product, and then we're in the same position that we were in number 1 there. So again, as long as I didn't make any mistakes when I did my math with this one, 17x plus 11y minus 6z equals 34. Okay, but that process is what we're doing. Find 2 vectors, which is a lot of options to do, find their cross product, and then go back and set things in. You guys probably understand why we show your work, but definitely make sure you show your work on things like this so that if there is a mistake, I can go back and kind of figure out what it is. I know your calculators can find cross products, so use that to kind of help out there, but I still want to kind of see the steps of what you're doing so I can go back and check if there's a mistake somewhere. Okay. All right. Other questions? We're ready to go to the notes. We have a little bit left of 11.6, and if we've got time left, we'll start talking about 11.72. So that image that I gave you guys, I should put this in the notes, and I'm sorry for not just having it in the notes. I really don't have a reason why I didn't. But anyway, here's the 6 different types of quadratic surfaces we can work with. I'm not going to go through all in great depth now. We know that there's relationships between these equations. There's some similarities, some differences, and if we can kind of reason through those, we may be able to identify the shape without having to go through a graphic here. And so we did that twice yesterday, and example 13 is going to go through it again. It's a more complicated shape there. But what makes these special, what makes these surfaces special is they're three-dimensional, which is why they're surfaces and not just shapes or curves. They all have a highest degree of 2. Nothing is beyond the degree of 2 there. And we are looking for different combinations of those quadratic terms combined into one equation here. Okay. So we left off, finish up that one. So page 37, example 13. Same directions as before, classify and sketch the surface. Again, we've got all 3 variables present, x, y, and z. The highest degree term we have is squared. Do we have an x squared and a y squared and z squared in this problem?
Yes.
Yeah, so we know we're not working with paraboloids. If we're missing a squared on one of those, we don't have a paraboloid anymore, or we don't have a, we have to have a paraboloid there. Okay. We can go through and kind of finish reasoning through what shape it is. So let me note this stuff down here. So all 3 variables are squared, which means it is not a paraboloid. We have to be careful with looking to see if we have a constant, because there's something different in this one that we didn't have before. What additional things does this problem have that 2 we did yesterday didn't?
Now we have all the 3 variables, but they are with constants and they have no degrees. I mean, their highest degree is 1.
Right, we've got those linear terms to the highest degree of 1 there. We didn't have those before. Do you remember what that means we're going to have to do?
Do we separate them?
We're going to have to go through and separate them or combine this together and complete the square. Okay. Whenever you've got those linear terms present with the quadratic terms, you're kind of stuck with completing the square to really see the structure of this thing here. So we'll have to complete the square for the x, we'll have to complete the square for the y, and we'll have to go through and complete the square for the z part of this, and then we can go back and see if we actually have a constant. Because remember, if we've got that constant of 3, if that really just changes but doesn't go away, then we know we're not working with certain forms. We know that we're not working with, well, I memorize that using cheat sheet. Okay, we can't have a cone. A cone can't have a constant with it. So for some reason, when we go through and complete the square, if our constant gets canceled out and is gone, we're working with the cone there. Or if it's still around, we can kind of classify this thing accordingly. So we really can't do anything else easily with this until we go through and complete the square. So let's do it. All right, if I just first rewrite my equation, I'm going to have x squared minus 4x plus 2y squared plus 4y plus z squared minus 2z, and I'll just leave that plus 3 over here. If you want to move to the other side, that's fine, whatever you're comfortable with. Okay. We won't do the completing the square on every single one of them. That's something I'll assume you guys know how to do. We'll review it once, and then I'll just give you the answer for the rest of them. If we think about the green stuff, the y terms there, can we just complete the square on those y terms right now, or do we have to do something ahead of time? I'm kind of asking the question weird. Let's ask it this way. What has to be the coefficient of the squared term before I can complete the square?
The square term.
So like this square term or this square term, this square term. What has to be the coefficient? 1. Has to be 1. If it's anything other than 1, we have to first factor that thing out before we can go through and complete the square. So on the x term, it's fine. We can go through and complete the square, figure out that missing pieces. On the z, we're fine. But on that y term in the middle, we would have to go through and factor a 2 out of both of those. So if I just rewrite this with that 2 factored out, it should be consistent. So we have to make sure we take care of that before we go through and do completing the square. Okay. All right, however, like I said, let's just do the x since it's listed first. Let's go through and complete the square for that. And then, like I said, I'm trusting that you guys have done this before, and if you will practice, remember how to go through and do it there. But to complete the square, we're looking for that special term that if I add it, it's going to make a perfect square to this. So how do I know what I'm going to add to this in order to make a perfect square out of that? Remember what we look for?
Divided by 2.
Yeah, and what are we dividing by 2?
And then square -4.
Yeah, that -4. So the middle term's coefficient, that b term, we're going to divide it by -2 and then square it. So -4 divided by 2, and I'll write it out the long ways here. If you're comfortable without showing all this, that's fine. We're going to have that term squared, and we're going to have to go back and subtract it to make sure that we are not changing the value of our equation there. Okay, and then I'm just going to ... the rest of this, because we're going to do more stuff for the y's and the z's. Okay, we hope that looks familiar. So you take your middle term's coefficient, or what will be your middle term's coefficient, divided by 2 and square it, and then make sure you subtract that constant as well. So that gives us x squared minus 4x plus -2 squared, which is +4. So +4 minus 4. And again, we'd have to do the same thing for the y terms and the z terms. It's going to save some time. I'll give you the answers in a minute. Keep in mind when you do this for the y term, all that stuff that's in parentheses is going to be multiplied by 2. So you will have to distribute that when you combine your constants together. But the nice thing about this is those first 3 terms should always give you a perfect square. And that's why we go through and complete the square like this. So in this case, it's going to give us x minus 2, the quantity squared. And then we still have that -4 left over. Right? Do we need to explain more stuff, or do we remember doing this a little? I didn't show every single step here. There's some things we kind of skipped. So yeah, if we take those first 3 terms, x squared minus 4x plus 4, and factor those, they're always going to be a perfect square trinomial. So the shortcut pretty much is just take the square root of your first term, the square root of your third term, and then carry down the middle sign. Looks familiar, Brett? Looks like you're thinking about it.
I've never been able to figure out complete square. Oh.
Okay, well,
I've seen it now, but I'm like,
all right, so we would do that for all of them. And again, if you want to go through and do more, we can. But like I said, I'm kind of assuming this looks familiar. So if we do that for all these terms here, eventually what we're going to end up with is this. We're going to have x minus 2, the quantity squared. When we do this for the y terms, we are going to have plus 2 times y plus 1, the quantity squared. And for the z, we'll have z minus 1, the quantity squared. And if I combine all my constants I get left over together, we end up with a 4. Okay, so like the -4 from that previous step, I have to add to both sides. The y would give me a constant, the z would give me a constant, and that 3 we have to the beginning. If I combine all those constants together, eventually I can get a 4 on the other side. Okay. So I would definitely say feel free to take this as something just to try on your own there, since you know what the answer is. And see if you can get to that point. If you can't, then we can go over it some more. One more thing before we try to go back and classify this. When we're working with quadratic surfaces or quadratic just whatever, constant of equal 1 is going to be a lot handier. So let's divide everything through by 4 to make this constant equal 1. And this has nothing to do with completing the square. This part is just that it looks more like those quadratic terms. So we have x minus 2 quantity squared over 4 plus 2's will reduce, so I can have y plus 1 quantity squared over 2 z minus 1 squared over 4 all equals 1. So the goal of why we did this was to be able to go back and classify. Like we said, all the x, y, and z's have a squared term. We know it's not a paraboloid. Are we left with a constant? Yeah, we've got this equal to 1 thing, or with 4 back up a step, which means that's going to kick out equaling a cone. So really what we're left with is either an ellipsoid or hyperboloid of 1 or 2 sheets. Okay. The difference between those 3 equations, the number of positive, negative signs we have here. Are all of my variable terms positive? The x squared, the y squared, and the z squared parts?
Yep.
Yeah. When they're all positive, think like circles. Circles, spheres have all those terms positive. This is going to give us an ellipsoid. Okay. Once we start throwing in negatives, that's where it kind of splits this thing off into pieces, either 1 or 2 sheets there. But this is going to be an ellipsoid. And like I mentioned yesterday, even if you didn't go through and classify this by doing it that way, technology is going to be able to graph this and you can see it. Our calculators just don't graph it very easily. Especially if you had that original equation we worked with. You're going to have to complete the square with that original equation in order to have your calculator have a chance at graphing this. You got to get z by itself there. Okay, so it's handy to be able to kind of know what to expect from this. Right? So we do have an ellipsoid. We could go into a lot of depth here saying what direction is the longest, the x, the y, the z, and all that stuff there, but we're not going to get that crazy. One thing you should be able to see, though, is where the center is. So where is the center of this ellipsoid?
2, -1, 1.
Yes, and how do you know that, Stephanie?
Because it's just like a circle.
And so we're looking at what we're yeah, so just like you do with the equation for a circle, x minus whatever that thing is you're subtracting, that's going to be your center. So 2, -1, since we're adding 1, 1. So that's the center of my ellipsoid. Okay. Let's mark that this is the center. We're not going to care about the foci. We're not going to care about the lengths of the axes, although you could get that information from here. If you remember how you did it back in Calc 2, it's all the same processes. Okay, but we're not going to worry about that. We just want to go back and sketch this now. When we sketch them, we'll do traces. We're still going to do that, but we're going to do one thing that makes it a little bit easier for us. All the traces we looked at so far are just like on the XY plane, or the YZ plane, or the ZY plane, those three kind of standard ones. Those would work here too, but they're not going to be the easiest to go back and actually work with this, because we're not going to do it this way, so if you don't write it down, that's fine. Let's just say if we were going to find the XY trace, we know that means that Z has to equal 0. If we go back and let Z equal 0 in this equation, does that Z term drop out, or does that Z term just produce a constant? Yeah, so it works, but now we're going to have kind of a more difficult equation to work with there. So what we'd like to be able to do is, instead of look at that XY trace, which isn't wrong, an easier trace to look at will be, let's say, what if we let Z equal 1? If we let Z equal 1, now what happens to that Z term? It's going to go to 0. It's going to drop out there, and that's going to make it a slightly easier thing to graph. So when we're thinking about this in terms of a trace, if we've got this three-dimensional space, remember Z moves things up and down. So instead of letting Z equal 0, we're raising this up to that plane where Z equals 1, and we're looking at the trace or the pattern that this makes on that plane. So a very similar idea, we're just going to kind of shift it since our whole shape is shifted, if that makes sense. So let's finish that. If Z equals 1, then what we're left with is x minus 2, the quantity squared over 4, plus y plus 1, the quantity squared over 2. That Z term is all just going to go to 0, and equals 1. Do you remember what shape this makes in 2 dimensions? Almost a circle, an ellipse. If we had the same denominators, we definitely have that. So this is going to give us an ellipse. And you can find the center, you can find the length of A, length of B, all that stuff there, but let's just remember it's an ellipse. Okay, I'm really bad at sketching this one, so I'm probably not going to try to sketch it. I'll just show you an image of it. But the idea is that we have on that plane that's raised up, we've got an ellipse that we're working with. In the x direction, it's going to be longer than it is in the y direction, just because the denominator for that one is a little bigger. And let's pick similar points there for the other ones. So let's go through, and instead of letting y equal 0, what's a handy number to let y equal to make that whole term cancel out? -1. Radio. So if y equals -1, x minus 2 squared over 4, plus z minus 1 squared over 4 equals 1. This one is a circle. Since both denominators are equal, we just have a circle there. So again, if we try to picture this, if we've got this three-dimensional space, and we can imagine that y plane, that y equals -1 plane, we're talking about making this a circle on this shape right here. So we've got an ellipse in one direction, a circle in the other direction, and if we check the very last direction, so x equals 2, we'll make that reduce down. We're going to have another ellipse. So again, if you're good at sketching, this one's a bit more difficult to sketch just because it's shifted. And when I tried doing it, no matter how I tried, mine just looked horrible, so I don't want to confuse you guys more. Okay, but if you can kind of picture this, we've got these different planes making ellipses or circles. We basically have an egg is really what we're working with here on this one. Okay. So I do have it graphed with the wonders of technology. Here we go. That's what that ellipse looks like. Okay. And again, if you try to imagine where the center of this thing is, so cutting it in the middle here, in the one direction on not the x, y plane, we raise that up to z equals 1, we had an ellipse. When we, this one had too much. When we turn this, so we were looking at the y direction, we had just a circle, and there's our circle. And then we were looking at it in the z direction, we had an ellipse.
So can you do that on our calculators, the TI-89s?
Sort of. to do it on a calculator, you have to have it in,
This 3D is in Z equals, so we'd have to Z equals it thing.
and that's why it's kind of a pain. I mean, it is doable, but you're going to have to go through, and if you start off with just the original equation, you're going to have to complete the square because Z shows up twice. So you're probably going to have to get to this point like we had here. But if you go through and solve for Z, you're going to have a positive and negative square root of a bunch of stuff here, and you have to graph both those parts. So yes, it works. It's just,
Sounds ugly.
yeah, it is ugly. And then to get a graph that's only mediocre, it's like, it's not really worth it. Like I mentioned last time, when you have to do this kind of stuff on a test or quiz, when I pull up these GeoGebra graphs, obviously you can't do it on a test. So I'll try to pick things that are simpler to sketch, things that you can do in your calculator are going to work out a little nicer there. Maybe I'll just ask you to classify, not actually draw it or something like that. I'll try to be a little more realistic when I give you things to do without the fancy technology. Okay. So yes, your calculator can do it. But like I said, it's just kind of.
Gotcha.
All right. Questions? Okay, so let's talk about another kind of shape that we can have in 3 dimensions. Those are going to be our quadratic surfaces there. Again, we can recognize them from just looking at the equation. We can see with the equation kind of what's going on there. And we've got all variables present, and the highest degree we have is 2. We know it's going to be a quadratic equation. If we back up before we get to this, if we back up a minute, when we were talking about those cylindrical surfaces, that's still going to generate some kind of 3-dimensional surface. Remember, something was missing. We were missing an X, or missing a Y, or a Z, or a combination of those. And that missing variable is basically my hint that, okay, I have a 2-dimensional shape that I've stretched in one direction here. So depending on the structure of the equation, we can kind of start to picture what these shapes are going to look like or get a hint of them. And this is another type of shape we can work with. Okay? So Calc 2, we do a lot of stuff with 3-dimensional shapes. But in all those things, all those 3-dimensional shapes we're working with, we took some kind of 2D graph and we rotated it. Okay, we were always working with surfaces of revolution. So we spent time working with surfaces of revolution. Revolving equations. I guess technically we revolve the graph of the equation, not the equation. Okay. So we found volume, we found surface area, we went through and found other things with this 2 centroids, but we were always taking something 2-dimensional and rotating it. So we never had to work with the third variable Z. X and Y are always sufficient there because we cut this up into a bunch of little circles. Okay.
So why do we do that? Why did we just work with third variable?
Because you don't need to. I mean, this isn't really simple. It only did in Calc 2. The simpler you can make math, the better. And not just for doing it, but like for programming, the simpler you can ask the computer to do something, the more efficient it's going to be too. It's simpler to do this stuff in 2 dimensions.
You know,
Depends.
everybody's saying Calc 2 so hard. I mean,
No, I know this isn't really hard so far, right? No, it's not really hard so far. I mean, it's different, but nothing's been difficult yet. And I'm going to warn you, it never really gets as difficult as Calc 2. Okay, we're not going to be that difficult anymore. Okay, but what we're going to do is we're going to say, okay, I have those 3-dimensional things that I'm making now. The whole point of Calc 3 is to be able to work with those 3 variables here. So how can I write an equation for that paraboloid, which is really what we were creating, but using my Z variable here? Okay. So remember, when we made these equations and we rotated them, we always were somehow working with circles. Whether it was like a cylinder or was a circle, we broke this down to circles a lot of the time here. And we know the equation for a circle. Okay, x minus the center squared plus y minus the center squared equals the radius squared. Okay. As long as the axis we were rotating about was the y-axis or the x-axis, it was much easier to work with. We didn't have to worry about sliding this thing and transforming it. So basically the center of our circles became just 0, 0. Just became like that axis of revolution there. And that's kind of the idea of what's going on here. So if we think about what we did with this, I kind of have some different directions there. But when we took some kind of shape and we rotated about the x-axis, so let's get something on the side here. So kind of follow this. If we go back to our Calc 3 or Calc 2 days, we had this. Let's say we had just a square root function and we were going to rotate about the x-axis here. Okay, if we turn this thing, we get kind of some like odd shaped cups and that opens to the side. But when we went through and sliced this, if we were thinking about using the disk method here, we had a whole bunch of little circles. Each one of those little disks has that same diameter, or that same radius, and that was generated by whatever the function actually was, right? And in a case like this, we rotate about the x-axis. We wanted the function then in terms of x to know what that height was. And that's really all this is saying down here. So we're going to kind of add that third variable. Again, we're making these circles. Now we do have the option for 3 dimensions. And so if I think about taking one of these disks that I would have created from this, if I pull one of those disks off, it's a circle in that X, or not, sorry, in that Y and Z plane, we have a circle there. And so here's the equation for a circle in the Y-Z plane, center at the origin, okay? And then what the radius is going to be, well, that's that function, that generating function that told me how big my disk was is just the radius. And if we rotate this on a different axis, the y-axis, the z-axis, the variables just kind of flip-flop places. But the idea is when I create these circles, these surfaces of revolution, we slice them, got a whole bunch of circles that are changing sizes. If we kind of squish them all against that one plane, they're all going to sit, like in this case, on that y-z plane, but the radius is going to be changing shape. A little bit of sense what's going on?
Yeah.
So when we're doing this, when we're writing surface of revolution or an equation for them, really the only things we have to know is what axis did we rotate it around to know which of these three cases we'll work with. And then we have to know what's called the generating function. Okay, so this part here, that is the generating function. Okay, it's what is that two-dimensional curve that is generating the radius for these guys here. I don't know why my graph doesn't show up. Did graph show up on your guys' notes here?
No,
Do you have what I have here? Yeah, there's supposed to be some kind of shape there. I don't know why it didn't work. It must have just exported it incorrectly. So let me graph this then. Oh. There's no super simple way to graph this without showing you the answer. Let me try one thing before I just. I was really hoping the graph showed up on yours and it was just mine that it didn't work on. Oh, I had to hide this. Okay, hold on. I don't want to give you the answer. I want to kind of build it from where we're going there. Okay. What do we have? Y equals 1 over Z. Oh, that's not going to work. Okay, never mind. X and Y. Okay, so let's write the equation and then I'll go back and show what the graph looks like. So 14 says find equation for the surface of revolution by revolving the function below by the z-axis. So if we just purely do this based on the math that's listed above there and not even worry about trying to reason through what's happening right now, we can. That'll be sufficient. So around the z-axis means that we know we are looking for something like this. X squared plus y squared equals some generating function squared or radius squared. It is just the equation of a circle. Radius is a bit more complicated. And since it's a z-axis, all those circles are going to be in terms of x and y. So that part's going to stay there. Really, all we have to go back and do is just replace that radius or that generating function here. And we want it to be in terms of z. And so it's just substitution. We're going to take that 1 over z function and we're going to plug it into this equation. And then if we simplify a little bit, we get that, and that's it. That's our final answer.
That's it.
That is it. It's pretty simple. Okay.
Cool.
Yeah, and this is a lot nicer than the other ones. So let me go ahead and graph that guy so you can see kind of what the surface looks like, and then I'll backtrack just a tad.
Does this one go to the
All right, there's a lot of stuff going on here. Let me change the color. Black is hard to look at. Okay. And let me see. Help, that made it worse. Okay, so it's kind of hard to look at this because we have such a mass plane here, but basically what's happening is we've got this function. If you think about 1 over x, okay, you can picture what the 1 over x function looks like, right? It's going to have an asymptote. You're going to kind of go off in 2 directions on this 1 over x. And that's basically what's happening here. So if I try to line this up, it's not quite going to look like it. Okay, but we can kind of see just the resolution's not great. We've got that 1 over x looking thing over here. And then in what would be the third quadrant, we have another piece over here. And so we took that, we rotated that whole thing about the z-axis, and it created kind of this weird plate thingy on top that would go up. The resolution's not very good here, but it would go up forever in this direction, and on the bottom would do the same thing too. So we got this really weird funnel-shaped piece on top and bottom is basically what's going on there. And that is it. I mean, there's really not much else to this. We've got this crazy surface of revolution on that plane there. Now, for this problem, it said y equals 1 over z. If the same thing was asked of us to get x equals 1 over z, the answer would be no different. So when we're working with these surfaces of revolution, there's kind of multiple ways we can generate them. As long as that radius is in terms of z, we don't care if it's x equals or y equals, it's going to work out. And so this next example kind of illustrates that too. And again, I don't know where the graphs didn't work. So find the equation of surface below, rotating the function about the y-axis. So if we're rotating it about the y-axis, what that means is we are going to want to have the equation. There it goes. Oh, goodness, pen. Yes, we're going to want that radius function in terms of y. Should be r of y. Sorry, I wrote the wrong thing there. So we're looking for r of y is what we're looking at there. Okay, we're going to the axis that you want, which means the other part, the circles, are going to be terms of x and z. So the left-hand side is going to be x squared plus z squared, and then we need some function for the radius in terms of y, and then we're going to go through the square of that. So the question now becomes, what is the generating function? What is my radius function in terms of y?
Square root of 9y cubed.
Close, only we're going to divide by 9.
Oh.
Right, but yes, everything else you said was correct. So solve that thing for x, get x by itself. So we're going to have x equals, technically it's a positive or negative square root of that. We can reduce that down to square root of 9, we know is 3, so we can rewrite that a little bit differently. But we're going to end up squaring this, so it really doesn't matter if there's a square root there or positive or negative. For our surface, we're going to go back and square this. So we're going to have x squared plus z squared equals, and I'll write it with that whole thing in place right now. Okay, but you guys know the square and the square will cancel out. And so this would be our equation. Okay. So they're not as complicated, they're a little simpler.
Can you show us how to graph these on the graphing calculator?
Yes, so to graph these in the graphing calculator, same thing like Stephanie was saying before, you've got to get z by itself. So once you've got this equation, you're going to have to solve it for z. So minus x squared from both sides and take the square root. You're going to have to introduce 2 functions. So you have z equals a square root of all that stuff solved for z, and then z equals negative square root of all that. Okay. So instead of going through it, I mean, you guys can do that, but solve this for z and enter both those as 2 pieces there. But instead of doing that, if we think about this shape in 2 dimensions, because really all we're doing is just rotating this. So the generating function we were working with was what, 9x squared equals y cubed? I still really like Desmos, this is like my favorite. Okay. So we've got this function here. We rotated it about what axis? The y-axis, it said? Mm-hmm. So you can picture this, when you think back to Calc 2, if you take this guy and rotate like the y-axis, you get this kind of really steep, I don't know what shape you want to call it, funnel shape again, but I'll bring them on a minute, okay? That's the same exact shape we're working with now, okay? We're just saying we're talking about in 3 dimensions, and so we have different equations, right? Okay. Well, an equation, we never had one before. Like 2 minutes left, let's finish this off so we're done with this chapter here. Like we said, these aren't unique. We can generate them by rotating about, depending if it's in terms of x equals or y equals, we can still go ahead and get this. So example 16, find the generating curve and the axis of revolution for the function below. So this could be written as a surface of revolution. This could be left as a quadratic surface. We've got options for this. Technically falls into both those groups there. But probably the easiest way to go through and do this is let's move this y term to the other side. Since x squared and z squared both have coefficients of 1, they're going to easily make that circle for us. So we have x squared plus z squared equals 9 minus 3y squared. Okay. Again, the only reason I did that is because we know to write a surface of revolution, we have to have something squared plus something squared. That kind of foundation for a circle, which we have here. Which means we can tell from either side here, what is the axis of revolution?
The y-axis.
And how do you know that?
Because there's no y in the x and z. Like this, the first term, there's no y in there.
Exactly. Okay, on that left-hand side, there's no y. That's one way you know. Or if you prefer to say my other side is written in terms of y, that's okay too. So it's revolved around the y-axis. The generating a curve, or the r, is just going to be the square root of that right-hand side.
Right.
Why did you pick y? Could you've done it with any term?
You could have,
Over.
no, because you want to have x squared have a coefficient of 1 and z squared have a coefficient of 1. So
Okay.
if I would have moved the z squared term over, there's really no way to get both those have a coefficient of 1 on them.
So if it was 3x squared instead of 3y squared, would you move the x one
Yep,
over?
if it was 3x squared instead of 3y squared, I would have moved the x squared over. Yep, exactly.
So why do you want to square root?
Because the generating curve, just the definition that we had up here, it said we had to take r squared. And so to know what that curve was, we have to undo the square and take the square root of it. Because like when we did here too, we were told the curve was 1 over z, so to find the equation, we have to square 1 over z. And this guy over here, we found the curve was the square of all that stuff, so we had to go through and square it. And so we're undoing that. Now if we're told that that other side, that r squared side is 9 minus 3y squared, we want to know what r is, so we're taking the square root of that to figure out what it is.
Then you don't you square R?
To find the surface, yes, but we're already told the equation of a surface. This question is like working backwards from what we did. We're saying, okay, here's the equation of a surface, work backwards to find out what the generating was and what the rotation was. So yeah, we're working backwards on this one. So there we go, that's it. Now we could write this as this equals x or this equals z, and both of them will be okay. So we've got multiple options here. Again, it's not totally unique. We can write it either way. This will work out. Okay, we are done with time. I don't know who has next classes after this. I don't want to make you guys late. If we have questions about it, I'm happy to talk about it tomorrow. I'll try to get your quizzes graded tonight so I can get them back to you quickly, but at least we went through and discussed them.
Are these, is this on the homework?
Yeah, all this is the last stuff on the homework, so you should be able to finish up with the homework after this information here. Tomorrow we'll start the next.
I'm gonna be gone tomorrow, so could you record the class?
Yes, I will make a note to that right now.
Okay, I appreciate it.
Yep, no problem. Thanks for letting me
Next week I will be missing, I think, Thursday and Friday. So Thursday, would we be able to like somehow send the quiz in the morning so I could go ahead and send it to you? So, or does it have to be in the
We actually won't have a quiz next Thursday because we'll be like just having finished this chapter, and so there won't be any information. So there won't be a quiz you're missing. You'll be good on that day.
All right, bless up.
Okay.
All right, have a good rest of your day.
Yep.
Doctor, just a quick question. I was doing the homework in Excel. I think they calculate this with the population, or so that's like a different first.
Yeah,
first
Excel
time,
has
different-
kind of like different built-in formulas here. Let me see if I have something.
Yeah, and I submitted the homework with,
Okay.
with the not the Excel one,
Okay.
but
Okay.
and it's like wrong in the grade.
Oh, so you did it online?
Yeah,
So I did. Yeah. Okay, I'll go back and take a look at it. I didn't even think about that being an option, but yeah, Excel's got different versions.
That's fine.
I'll go back and
Just
take a look.
like
Let me know. No, I didn't. I did not get an email.